delta phi not equal to 0. What's the answer? What goes into a flux? The area and the stuff. In other words, the magnitude of the stuff, right? So is the flux changing?
Yes.
Yes. Why is it changing? Is the area changing?
No.
Not in this case. What is changing?
The magnitude as you get closer to the
Magnitude
wire.
is changing, right? The field is getting stronger as I get closer to the source. So, yes, that is true. Now, of course, it could be getting weaker, but that still answers this question with a yes. Changing doesn't mean stronger or weaker. It could be doing either one of them to be changing. Okay? Assuming the answer to that question is yes. Is it increasing or decreasing? What's the field doing? The field through that loop, is it getting stronger or weaker?
Stronger.
Stronger as I get closer to the source. So is the flux increasing or decreasing?
Increasing.
Increasing. Okay. Now, it's not always the case. It's just in this particular case, it's increasing or decreasing. Right? In this particular case, it's increasing. Okay. Yeah. As it turns out, nature wants to do the opposite, right? This is not a physics rule. This is not the law of physics, but it's a good guideline. Nature hates change, right? Me too, I get it, right? My wife moves stuff around, I'm like, where's my stuff, right? Nature hates change. That's the essence of Newton's first law. In the absence of an external force, an object is going to keep doing exactly what it's doing. Right? Nature hates change. There's no difference here. If the flux is changing, nature does not like that. Right? So, if the flux is changing, nature wants to make the flux do the opposite so that it stops the change. Right? So you asked if it's increasing or decreasing. No matter what your answer to that question is, nature wants to decrease or increase. If the flux is increasing, nature wants to decrease it. If the flux is decreasing, nature wants to increase it. I will point out, nature fails every time, but she gives it her best, right? She tries. But that's the whole crux of this argument. Increasing or decreasing? Well, whatever it's doing, and remember, we wouldn't have even got to this question if the answer to the previous two weren't yes. If the answer to number one or number two is no, we're done. If the answer to number one and number two are yes, and then you answer number three, how is it changing? Increasing or decreasing? Whatever the answer is, nature wants to do the opposite. Now, how do you do that? How do you decrease a flux? Well, nature's only recourse is to decrease it by trying to induce a field which points in the opposite direction. Right? In other words, in this case, the field is pointed out of the page and it's increasing. Nature wants to decrease it. So nature needs a field to come in and go into the page, right? Out of the page and into the page. These are vectors. That's going to decrease the field, which means it's going to decrease the flux, right? That's not the only way flux can change, but it's the only way nature can do it. Nature needs to produce a field that's acting oppositely to this one, right? Now, if the flux was decreasing, nature would want to increase it. So she would need a field that would come in to go the same way. But in this case, nature wants to decrease the field. So nature needs a field in the ring that looks like that. Does that make some sense? Or at least, we haven't said why this happens. So we're just saying, if we take it that nature hates change, nature wants to stop the change. In this case, what you told me is the flux is increasing, and nature wants to decrease it. So nature needs a field to come in the middle of that ring and go the opposite direction. how does she do it? Well, where does any magnetic field come from? Moving charges. Well, I have a metal ring. That seems like a good place for a moving charge. So nature comes in and induces currents in this ring that will produce this field, right? What produces this field? Well, thumb in the direction of what's straight, that's the field. Means the fingers tell you the current that needs to flow in this ring to produce that field. Now remember, this is just a metal ring. I took a piece of rebar and folded it over and dropped it. I didn't connect any batteries to it. Why is there a current? Turns out, this is what happens when you have a changing magnetic flux through a loop of conducting material. If the flux is changing, that's a big part of this. The flux has to change. If it changes, nature wants to counteract the change. She induces an EMF. In other words, it's almost like nature hooks up a battery to this ring that makes current flow in a particular direction in order to counteract the change in flux. Right? So here's what happens. I take this ring with no current flowing and I drop it. All of a sudden, after I do that, there's a change in flux due to this background magnetic field. As the thing gets closer to the wire, the flux increases. Nature says, nope, not doing it today, right? So she has to counteract the change, or she has to try. So she induces a current, or I should say she induces an EMF in the ring, which then produces an induced current flowing in that direction, which produces an induced field in the direction of the green to try to counteract the change. Right? So this current, which is just from the wire, ends up making this current flow. This is normal I. This is my induced current. So current flows around that ring, not because I hooked up a battery to it, because I dropped it in a magnetic field and nature hates change. Okay? Now I'm just making all this up. This is all experimentally observable. And in point of fact is the way that 99-point-something% of the world's electricity is produced. This is a generator. Right? We all like electricity. We use a lot of it, right? There is some electricity in the world produced by solar power. There's some produced by geothermal. And those are the only two ways of producing electricity I know of that don't use this idea, right? Solar power requires chemical reactions, geothermal, also chemical reactions. Every other method of power production, as far as electricity, uses this idea to produce electricity because that current that's in the ring just came along for the ride. If you can harness that and then move it somewhere else, you can do things like power cities, charge cars and whatever, right? So this turns out to be a really, really important thing. Now, normally we don't do it by dropping rings, but that's not the point of this. The point of this is to show you something that you can easily see. There are other ways to change the flux. Take from this, if there's a flux through a closed loop of conducting material, and if that flux is changing, I should say a magnetic flux, and if that magnetic flux is changing, by golly, there's going to be a current induced in that ring that you can then harness to do things. Okay? Let me give you a more concrete example. Another background magnetic field, right? I'm not drawing the source of this here because I don't care. All right, let me take another loop. But this time, I'm going to connect that loop of wire to an armature that goes outside of the magnetic field. And I'm going to use that armature to turn that loop with some angular velocity omega. Now Now let me ask you the same series of questions. Is there a magnetic flux through that loop? Yes. There's a field there. Is the flux changing? Remember what flux, right? I didn't write this down this time. But flux is the same as it was with electricity. B dot A, where A is that area vector, right? What is the definition of this? Magnitude of B, magnitude of A, cosine of the angle between them. So the flux can change in 3 ways. The magnetic field could change. That's what happened in the previous example. The area could change. That's not happening in either of these examples. The angle between them could change. That's what's happening right here. We've got an angular velocity. So this thing turns and presents more or less of its cross-sectional area to the field. Therefore, the flux is changing, right? So you take a coil of wire, you stick it in a magnetic field, and you spin it, and lo and behold, you get electricity out of it. This is every generator. This is every electric motor, just working the other way. This is your alternator in your car. This is the windmills in West Texas. Well, I'm from East Texas, but we drive past a lot of windmills. This is a turbine turning in the Hoover Dam, or a nuclear fission power plant, or a nuclear fusion power plant, if those ever come online. This is how electricity is produced. You take a coil of wire, you rotate it in a magnetic field, you get electricity. It's a little bit more complicated than that from an engineering perspective, but from a physics perspective, that's what you got, right? It comes from the change in flux. The change in flux always produces an induced current that tries to counteract the change in flux. Right? This is called Faraday's law. And I'll give it to you like your book is. Well, I'll give it to you in simple form. Induced EMF, right? We know that to produce a current, you're going to have to induce an EMF. You're basically going to have to connect it to a virtual battery. Induced EMF is equal to minus, I'm going to leave a little space, you leave one too, d phi b dt. Time derivative of the flux with a negative sign. The negative sign is an indication that the change that nature is seeking to counteract the change in flux. Generally speaking, if you're working numerical problems, we ignore it because all we're interested in is the magnitude of the EMF, but it's still there. You should understand what it means. So take the time derivative of the change in flux, which means the flux should be expressed as a function of time. It gives you your induced EMF. Now, I've left a space because in most of the situations that you deal with on a practical basis, you're dealing with not just one loop of wire, but a coil. I told you solenoids were going to be important, right? If you've ever taken apart an electric motor, there's wire wrapped all around it. There's tons and tons of turns. If you ever looked at your alternator, there's lots of wrapped wires, right? So this is the usual way to beef up a generator or a motor is to put in multiple turns of wire. So I'll leave a space here, and what I'm going to put here is a capital N for the number of turns of wire. Now, in a lot of the problems we do, there's only one loop, so N turns out to just be 1. I'm putting it here because it's the way your book does it. In general, you should understand it, right? So this is the idea that this is the change in flux through one of these turns. You multiply that by however many turns you have, and this is your induced EMF. Now, again, there are 3 different ways the flux could change. The field could change, the area could change, or the angle between the field and the area vector could change. The first example we did was the case where the field was changing, right? Or at least the field through the loop was changing. The second one, we didn't do any problems here, we will. But this is the idea where the angle between them is changing. There are some situations in which the area itself can change. But any one of those 3 changes in flux will result in a current being induced in the wire. This is Faraday's law of induction. named after Michael Faraday, same one the Farad is named after. Law of induction. What is typically straightforward about this is its actual calculation. What usually causes students some consternation is figuring out what direction currents have to flow to produce the desired change. We'll get into that next time. Any questions about this?
Is that saying like if I spin, if I change the link faster, I will produce more current?
Oh yeah, that's a good point. Yes, absolutely. Because this is not just proportional to the change in flux, it's proportional to the time rate of change in the flux. So if the flux is changing faster, yeah, you get a